whole of this lecture. Today I will see quadratic form and various type of quadratic form. We all of us know positive definite, positive semi-definite, negative semi-definite, indefinite. This is the various type of quadratic form. Today I will discuss this part elaborately, just as a review. In my previous video, I had discussed this topic elaborately, but today's topic, actually just as a review, I will discuss again this topic because this topic is very important for any competitive exam. At first, let's see what is the quadratic form, just as a review. We all of us know the quadratic form is self-bilinear form. Let V be a vector space over the field F. A function A is from the set V cross V, ordered pair of vectors to the field F is called bilinear form on V if A is linear in each variable. When A is linear in each variable, where A is be a mapping from V cross V to F, where F is field. When the other variable is fixed, then A is called. When A is linear, one variable, then other variable would be fixed. Then A is called bilinear form on the vector space V. Here A is be a mapping from V cross V to F. Here first A is linear with respect to first coordinate, then other coordinate would be fixed. Then A is mapping with respect to the second coordinate, then first coordinate would be fixed. A is ax1 plus x2 comma y equal to A is x1y plus A is x2y, and A is ay1 plus y2 equal to A is x comma y1 plus A is x comma y2, where x1 y1 x1 x2 y belongs to vector space and A belongs to field. Example, A is equal to x transpose ay. This is be the bilinear form, and quadratic form is actually the special type of bilinear form. This is the bilinear form in itself. That means A is x with itself. That means qx equal to A is xx, which is equal to x transpose ax. This is equal to summation ij running from 1 to n aij xi xj, and this is be a polynomial of second degree. This is be the polynomial of second degree. As for example, if you consider qx equal to x1 square plus x2 square up to x3 square, then that imply x1 x2 x3. Here the mapping, here the matrix A equal to 1 1 1, other part would be 0, and here x1 x2 x3. This is the transpose, because quadratic form is always x transpose ax. That means quadratic form is actually special type of bilinear form. This is actually second degree polynomial, where obviously this A is symmetric. Now I will see when a quadratic form is positive definite, positive semi-definite, negative semi-definite, indefinite. Quadratic form is different type: positive definite, positive semi-definite, negative semi-definite, and indefinite. And positive definite means first f of x1 x2 up to xn greater than 0, strictly greater than 0 for all x1 x2 xn belongs to Rn. And positive semi-definite means f of x1 x2 xn strictly greater than equal to 0, and this is true for all non-zero x. Here Rn minus singleton set 0, and positive semi-definite means this is greater than equal to 0 for all non-zero x. Negative definite means f of x1 x2 xn 0 less than 0 for all non-zero x, and negative semi-definite means this value is less than equal to 0. Here equal to sign, less than equal to, semi means always equal to for all non-zero x, and indefinite means both, either f of x1 x2 xn strictly greater than 0 here, not for all, here for some x, and f of x1 x2 xn less than 0 for some x also. Okay, that means positive definite means function is strictly greater than 0 for all non-zero x. Positive semi-definite means function is greater than equal to 0 for all non-zero x. Negative semi-definite means function is less than 0 for all non-zero x, and negative semi-definite means function is less than equal to 0 for all non-zero x, and indefinite means function is greater than 0 for some x and function is less than 0 for some x. That means for some value of x this value is less than 0, and for some value of x this value is less than, greater than 0 and less than 0. This is the first criteria of positive definite, positive semi-definite, negative definite, negative semi-definite. And for example, if qx equal to x1 square, x2 square, x3 square, then this value is always strictly greater than 0 for all non-zero x1 not equal to 0, x2 not equal to 0, and x3 not equal to 0. So this quadratic form is positive definite. Second, if we consider qx equal to x1 square plus x2 square plus 2x1 x2 plus 2x2 x3 plus 2x1 x3, then this value equal to, we can write x1 square plus x2 square plus x3 square plus 2x1 x2 plus 2x2 x3 plus 2x1 x3 minus x3 square, which is equal to x1 plus x2 plus x3 whole square minus x3 square. Then there exists x1, x2, x3. For that, x1 plus x2 plus x3 square strictly greater than 0, and there exists x1, x2, x3. For that, x1 plus x2 plus x3 whole square strictly less than x3 square. As for example, if we consider q1, 1, 1, this value would be 1 plus 1 plus 1, 3 whole square 9 minus 1, this value is 8, which is strictly greater than 0. Similarly, consider q0 minus 1, 1, this value is 0 square minus 1, which is equal to minus 1, which is strictly less than 0. Therefore, since for this value is greater than 0 for this vector, also for this vector this value is less than 0, so obviously qx is indefinite. Another form, if qx strictly greater than 0 for all non-zero x, that means x transpose ax is strictly greater than 0 for all non-zero x belongs to x. Positive semi-definite means x transpose Ax strictly greater than equal to 0. Negative definite means x transpose Ax strictly less than 0. This is true for all non-zero x. Negative semi-definite means x transpose Ax less than equal to 0 for all non-zero x, and indefinite means x transpose Ax strictly greater than 0 for some x and x transpose Ax strictly less than 0 for some x also. Another method of positive definite is eigenvalue of the matrix A are all positive, and for positive semi-definite, eigenvalue of A, matrix A, where A is symmetric matrix, are all non-negative, and determinant of non-negative means it can be 0, the eigenvalue can be 0 also, and determinant of A is equal to 0. For negative definite, eigenvalue of A are negative. Negative semi-definite, eigenvalue of A are non-negative and determinant of A equal to 0. And indefinite, eigenvalue of A are positive as well as negative. Another test of positive definite is minor test, privious minor test. If D1 equal, privious minor test means D1 greater than 0, D2 greater than 0 up to D3, Dn, so on. This is greater than 0. Where D1, D2, D3 is the determinant, we all of us know this is. Negative semi-definite, positive semi-definite means D1 greater than 0, D2 greater than equal to 0 and D3 strictly greater than equal to 0. That means at least one of Di equal to 0. And negative definite means D1 greater than 0, D2 greater than 0, D3 less than 0. That means first D1 would be less than 0, then D2 greater than 0, then D3 less than 0. That means alternative sign, but first principal minor should be negative. This is a very important part. First principal minor should be negative, then positive, then negative. And negative semi-definite means D1 less than 0, D2 greater than equal to 0, D3 less than equal to 0. That means at least one of Di equal to 0 for I equal to 1 to up to n. And if none of above case happens, then this is called indefinite. As for example, consider A equal to this matrix. Then this is D1, this is D2, this is D3 and this is D4. Notice D1 equal to minus 1, which is negative. D2 equal to plus 1, which is positive. D3 equal to also minus 1, which is negative. And D4 equal to plus 1, which is greater than 0. Since alternative sign and D1 less than 0, then D2 greater than 0, then D3 less than 0, then D4 greater than 0, that means this is negative definite. This quadratic form is a negative definite. Okay. Next, consider the matrix. The matrix is, this question has come in session net exam. The matrix is positive definite, second non-negative definite but not positive definite, third negative definite, fourth neither negative definite nor positive definite. For this, here I will use the principal minor test. Notice, first minor is positive, second minor is D1 is equal to 3, which is greater than 0, D2 equal to 6 plus 1, sorry 6 minus 1, this value also greater than 0. That means since both D1, D2 both greater than 0, so since D1 not less than 0, so negative definite cannot possible, either positive definite or indefinite. Then D3 this value would be 3 times 6 minus 1 determinant of the 3 minus plus 1 times minus 3, and this value would be 12, which is strictly greater than 0. Since D1, D2, D3 both strictly greater than 0, that means this matrix is positive definite. Have you understood? By minor test, we can tell easily is any matrix be positive definite or negative definite or positive semi-definite or indefinite. Okay? Oh well. Now, let's see one question which had come session net exam. Consider Aij be real symmetric 3 cross 3 matrix and consider the quadratic from Q x1 x2 x3 equal to x transpose Ax, where the vector x equal to x1 x2 x3 transpose. Then which of the following statement is true? Option 1, if Q x1 x2 x3 is positive definite, then all Aij greater than 0 where I not equal to j. If second option, if Q x1 x2 x3 is positive definite, then Ai equal to 0 means all diagonal entries are strictly greater than 0 for all I. Option 3, if Aij is strictly greater than 0 for all I not equal to j, then Q x1 x2 x3 is positive definite. And option 4, if Ai strictly greater than 0 for all I, then Q x1 x2 x3 is positive definite. Which of the following are true option? I hope my all viewers have understood the question. We all of us know this is the result. If quadratic form is positive definite, then always the diagonal element Ai greater than 0 for all I. Because Q x1 x2 x3 is positive definite means x transpose Ax strictly greater than 0 for all non-zero x. Consider arbitrary vector e1, e2 and e3 and consider arbitrary matrix A. Then e1 transpose A, e1 means this, and since this is the positive definite, so always this value greater than 0, strictly greater than 0. After calculating this value is a1 strictly greater than 0, a11 strictly greater than 0, and e2 transpose a2 means 0 1 0 transpose this matrix, and this means a2 to that imply since this is the positive definite, this value is strictly greater than 0. After calculating this value would be a2 to strictly greater than 0, and e3 transpose e3 means this is the e3, this is the arbitrary matrix A, that imply a33 strictly greater than 0. Therefore, if Qx1 x2 x3 is positive definite, then always Ai strictly greater than 0, and this is true for all I. Not only positive definite, this result also true for all definite matrix. Actual result is when A is positive definite, then all diagonal entries is strictly greater than 0, because when the matrix is positive definite, then the matrix is symmetric, and we all of us know in symmetric matrix diagonal entries are actual the eigenvalue of the matrix, and when A is positive definite, then all eigenvalue are positive, so Ai is strictly greater than 0. Similarly, when A is negative definite, then Ai is strictly less than 0. When A is positive semi-definite, then Ai strictly greater than equal to 0. When A is negative semi-definite, then Ai less than equal to 0. But converse need not true. When 1 3 minus 4 5 then we cannot tell, since the diagonal minus 4, 4, the diagonal entries are positive, but we cannot tell about the matrix is positive definite or not. Converse need not true for all result. Only for true indefinite matrix for independent. If aii aj less than 0 means if the matrix is given such type, here the eigenvalue are 1, -4, -7. Since ai aj less than strictly less than 0, then we can tell obviously the matrix is indefinite matrix. Converse true only for indefinite matrix, not all other case. Okay, so option 2 is a right option. Option 4 and option 3 is also wrong, because few minutes ago I have told you converse not true. If ai is strictly greater than 0, then we cannot tell the matrix is positive definite. As for example, consider a equal to 1, 1, 1, 1, 1, 1 and 1, 1, 1. We all of us know a quadratic form is positive definite if all leading principal minors are strictly positive. Here notice 1, first principal minor strictly greater than 0, but second principal minor 1, 1 equal to 0. Also third principal minors 1, 1, 1, 1, 1, 1, 1, 1 is equal to 0, since two rows are identical. So since all leading principal minors are not equal to not greater than strictly greater than 0, so this is not positive definite matrix. But all aij is strictly greater than 0, since all ai when I not equal to z, also all ai strictly greater than 0. Okay, so by this example we can break down the option 3 and 4. Option 3 and 4 also wrong option, only option 2 is the right option. I hope my all viewers have understood. This type of question actually very important for any competitive exam. Today I will stop here. In my next video I will discuss some more result about positive definite matrix, positive semi-definite matrix, negative definite matrix and negative semi-definite matrix. Because this type of result actually very important for any competitive exam. Okay, see you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.